How's everything?
Hey, Joseph. How you doing?
Yeah.
Good morning.
Doing well. Good morning. Okay, so we got about, what, 14 people here, so we can start. So looking at this lecture 11 on convolutional nets for NLP, a lot of us have already seen the concept of a convolution applied in image problems, and it's very similar with NLP problems. Even though it's a one-dimensional, it's actually a one-dimensional convolution, but it looks a lot like a two-dimensional convolution. Is everybody seeing the screen that I'm sharing, which is the presentation,
Yes.
the PDF? Okay, great. So I'm just scrolling. He talks about this book, which was new last year. It looks like it might be a good book on doing NLP with PiTorch, but I haven't looked at it yet. Apparently for Stanford students, they can actually sign it out from their library. So he starts on CNNs by reviewing the concept of convolutions applied to images, and you remember that you'll have a filter. In this case, it's a 3x3 filter that gets passed over every part of the image, and for each pass, for each position of the filter, and in this case, the filter is given by these red numbers. And so for each filter position, you multiply, you basically do a Hadamard product of the filter with the portion of the image that it's overlapping. A Hadamard product is, well, it's just multiplying multiplying number by number, and then adding all of those numbers together to get the final number. So here you can see how it works. 1 times 1. The contributions to this 4 are 1 times 1, 0, 1, 0, 1, 0, 0, 0, and 1. There are 4 ones, and they add up to give you a 4. And then you would move the center of the filter to the next pixel here, and then you would have these 9, this is a 3x3 convolution, it would be overlapping these 9 pixels. And then you would multiply each element in this overlapping 9x9 region of the picture with these 9 values and add them all together to get the next number that goes here. And so if you apply this, and you can see that there are 3 possible positions. You can slide this 3x3 filter 1 position over, and that gives you this number. You slide it over another position, and then that gives you this number. And then so there's only, you can only go 2 to the right, and then, but you can also go 2 down. So, you know, there are another 2 possible numbers, another 2 numbers that you get from moving the filter down here and here and filling in those 2 numbers, and then you can move over 1 and over another to get these 2 numbers. So, yeah, so this 3x3 filter passed over a 5x5 block gives you a 3x3 result for the and I think they would call that a feature map. Yeah, so is everybody clear on that, or are there any questions on how that works with 2D images?
I have a question. How do you choose these numbers with which, how to multiply them?
Okay, so the filter we're talking about is a 3x3 filter, and it's represented by these numbers in red, right? So it would be it would be 1, 0, 1, 0, 1, 0, 1, 0, 1.
So is there a pattern to it, or it's arbitrary numbers?
There's actually a pattern, and it's you know, and in this case the pattern, you can see the pattern is there's 1s on the edge and a 1 in the center. And typically these convolution filters with you can actually design convolution filters to detect edges or diagonal features and so on. But for now, we don't need to worry about the details of why these numbers are there. Just imagine that there's this 3x3 convolution filter that we want to apply to this picture. So does that make any sense to you?
Yeah.
Okay, so then the operation would be to multiply element by element the filter with the pixel values that it's overlapping. So 1 times 1, 0 times 1, 1 times 1, and so on. And so then you get 9 numbers, and then you add them up, and it gives you 4. And then you move the filter over 1 and do the same operation, adding together those 9 numbers to give you, first taking the product of the filter values with the overlapping pixel values, then adding that and get the number that goes in there, and so on. Okay. Someone else had a question? No. Okay. Let me look at there's a chat going on here. Let me see what's going on in the chat. Okay, everyone started the class. Why is it an X? Oh, why is it an X? That's a good question. There is a pattern in that convolution, and as somebody noticed, it's an X. The ones go across diagonally. So I imagine that this convolution does things like detecting diagonal features, although I'm not certain about that. But yeah, there is a reason. I mean, there is a reason. Sometimes they impose a set convolution filter. Other times you actually solve for the values as weights in the problem. So they would actually solve for the filter values. So yeah. Someone else, Dan. Well, welcome, Dan. Yeah, we're halfway through, but it's still, yeah. Let's see, the numbers in the filtering kernel are learned when you train. Yeah, sometimes they are learned when you train. Sometimes they are, sometimes the number in the filters are learned when you train. Other times they're just set beforehand and they're constant, static. Okay, so here's how a one-dimensional convolution is applied to text. So let's remember so we have a sentence, tentative deal, part of a sentence, tentative deal reached to keep government open. And then we imagine that each word is encoded by a 5-dimensional vector, although we know that, in real life, these vectors tend to be much longer than 5. 300 is more common, but for a small problem to illustrate it, it's fine to have 5. So, and then the idea is we have a filter of size 3, and so the one-dimensional convolution is in this direction, but you have to have a set of filter values for every dimension in your word vector, right? So this is a 4-dimensional word vector. In other words, each word is represented by a 4-dimensional vector, and so there's a one-dimensional convolution for each element in the vector. So it ends up looking like a 2-dimensional convolution in a sense, except we only have to process it in one direction. In other words, we only move downward. We don't have to move across and down like we did with the other one, with the 2-dimensional. Remember, back here, we had to move in both directions, and that's the difference between a 2-dimensional convolution and a 1-dimensional convolution. So you might see, but there's a 2-dimensional matrix here, so why don't we call this a 2-dimensional convolution? But the reason is that we only move when we pass this filter over the text, we only move in one direction. We just move downward. Okay, so the way this would work is you would take this filter, you would pass it, or you would line this filter up here so that it's overlapping these elements. Then you would multiply element by element all the values in the filter with all of these values that are overlapping. So so for example, the first entry would be 3 times 0.2 minus 0.5 minus 0.1, so that would be minus 0.2 from this operation. But then you have to do the second filter, 1 times 0.1, 2 times 0.2, 1 times minus 0.3, and add those together, and that gives you another number. And then you do this and this, that gives you a third number. This over this gives you a fourth number. Add all of those 4 numbers together, and you get this. So that's how this thing works. Does everybody see that? It's too bad that we didn't do the intermediate calculation. We could actually do that to verify for ourselves. In fact, it's a good idea. Let's do that to verify for ourselves that we really get -0 there. Let me see if I can, annotate a little bit. Bring out a pencil.
Joseph, I have a quick question.
Yeah. Yes.
Does the filter have to be always as long as the word vector dimension then?
Yes.
So if my word vector is 300, the kernel will also be 300 numbers
Yes.
long. Right?
That's right.
Okay.
Yeah, it's a one-dimensional convolution. So you have to have, so this dimension is already fixed by the dimension of your word vector. Okay,
right.
So
okay.
Yeah. So let's verify for ourselves that we do get this number here. And so we have 0.2 times 3 is 0.6, minus 1 times 0.5, and minus 1 times 1, that gives us a, for this first set of numbers overlapping with this, overlapping with this piece of the filter, we get what? We get it's just 0.
Minus 0.5.
0.6 minus 0. Sorry, 0.5. There's got to be a better way to do this. Minus 0.1. And so that first number is what? No, that's not right. Yes, it is right. So you get 0.6 minus 0.5 minus 0.1. That gives us a 0 for that part. So that number gives me a 0. And then I have to do the same thing for this one. So I'll get, let's do this in our heads. 0.1 times 0.3 is 0.3 minus 0.2 minus 0.3. So that would be minus 0.2. So this number we already said was a 0. This number we just said gives us a minus 0.2. And then we can do the same thing here. Does everybody see what we're doing here?
The second one be shifted, Joseph?
Pardon? Oh, you're right. I'm doing the wrong operation. I have to multiply these 3 numbers times these 3 numbers, and that gave me the 0. Now I have to multiply. Sorry. So Gautam pointed out these 3 numbers overlap these. So now I have to multiply element by element and then add together, right? So we get 0.1, 0.4, and minus 0.3. So that would be 0.2. So this first one was a 0. The second one is 0.2, right? And for the third one, we have to multiply these 3 numbers with these 3 numbers, right? So that's minus 0.6 minus 0.3 plus 0.2. So that's minus 0.7. 0.7. You can check me if you're listening. So my third number is minus 0.7, and let me just check that. Minus 0.6 minus 0.3 is minus 0.9 plus 0.2. Yeah, and then finally the fourth number. These 3 numbers multiplied by these 3 numbers, right? And so that's minus 1.2 plus 0.3. So that's minus 0.9. Plus 0.4, that's minus 0.5. So I have minus 0.5. So my 4 numbers are 0 plus 0.2 minus 0.7 minus 0.5. Let's see, is that right? Sorry, that's not minus, that's plus. So that's 0 plus 0.2 minus 0.7 minus 0.5, and that's equal to minus 1. Does everybody follow that? I know it's a big mess the way I did it, but we have 3 numbers. Let me just draw them above. We found out that this number was 0. This number was the number from applying the convolution filter to this column is 0.2 minus 0.7 and minus 0.5. So those are the 4 numbers that we got. We added them all up, and that's where we got the minus 1.0. Okay. Let's see. So then of course the next number would be you slide this kernel down to overlap the next 3, and you do the same operation again. You get 4 numbers. these overlapping three rows, and then you add them together to get that number, and then you slide it again. You slide it down one more, you get another number, and you slide it down another, you get the fourth number, and then you slide it down another position, and you get the fifth number. So it's basically just sliding this filter downward one row at a time and adding up all of the overlapping products. Is that clear enough? Okay, then.
Joseph, quick question. Is there any reason why they don't do the shift horizontally, just like the CNN for images?
Well, because the words, we're looking for relations among the words, and it doesn't make sense. And for one thing, the filter size makes it impossible to slide horizontally, because the filter size is by design, it has the same number of columns as the length of the word vector. So you can imagine that this filter is kind of locked in place. There's nowhere for it to go sideways.
Right, and is there any reason why they design it like that?
Well, because they're looking for relationships among words, and so it doesn't make sense to slide it to look for relationships among columns of the word vector.
Got it. Thank you.
Okay, so let's see. Erase all that stuff. How do we do that? Clear my drawings there. Okay, so then he talks about, and you're familiar with this if you've seen. Sorry, I got to get my pen back. Yeah, get my pen back. There it is. Yeah, so you're familiar with padding if you've seen this convolutions done with images, but it's the same idea. In other words, if we did it this way, we have 7 words in the sentence, but we end up with only 5 possible values for the convolution, and that's just because we're limited by a length 3 convolution only has 5 positions. You know, you can only move downward 5 positions, so you only get 5 numbers there. But what if you wanted the same number of results there as you have words? Then you could add 0 padding, just basically add a row of zeros before the beginning of the sentence and after the end of the sentence, and then then you have the 2 more positions to use. So now you can get what is this number of words? 7 words. You can get 7 positions in your feature map, and you can see how it goes. They're labeling the positions here from 0 tentative deal, so that's 0 TD. That's what that means. It's the number that comes from overlapping the filter with the first 3 rows. The next number comes from overlapping the filter with TDR, tentative deal reached, and that's this. Okay, and so on. So that's how padding works. It allows you to get, you can expand the number of values in your feature map. And if you wanted to, you could even add another row, and that would give you a feature map that has more features than words in the sentence. Okay, so that's the concept of padding, of 0 padding, and then and now the concept of more than 1 channels. So you could. There's no reason why you're limited to 1 filter. You can apply three filters of size 3, and then you would get 1 column for each filter. So that's the first column would come from applying this filter, passing it downward this way, and you get all these numbers. And then the second filter, passing that second filter over the same array of numbers, gives you the numbers in this column. And then finally, the third filter, passing over the same data, gives you the third column. So 1 column for each filter. Okay, so that's the concept of multiple filters, which we also have seen if we've seen convolution applied to images. But if you haven't seen that, it's the same idea. Okay, so
Joseph?
yeah.
So on the bottom right there, what does mean word? Also use 0 padding equals to, is that one sentence?
Sorry.
That part of the right, the words could also use 0 padding equals to, also called wide convolution.
Yes.
What's that word?
Let's see. He says if you use 0 padding, if you use 2 rows of 0 padding, that's instead of just 1, then you have a convolution that gives you more, that gives you a wider result than just the number of words in the sentence.
So,
right?
So by padding equals 2, you actually mean 4 padding, like 2 on the top and 2 on the bottom?
If you would put 2 rows of zeros. One, you'd add an extra row here and an extra row here, and then what you would have is an extra row here, right? And that gives, so you've got instead of having the same number of elements as in the length of your sentence, 7, yeah, you'd end up with another 2. So yeah.
I mean,
so that's what they mean by a wide convolution, I guess. Yeah.
Yeah, the padding size of 1 actually means 1 at the top, bottom, and 1 at the top, right?
Yeah, that's right. That's right. So a padding size of 1 would be 1 row at the top and 1 row at the bottom. Okay. And so he's talking here about adding an extra row on the top and an extra row on the bottom. Yeah, that's a good point. And then the wide convolution means you end up with wider. In other words, you get more elements in the feature map than you have in the sentence, in words in the sentence. Okay, so that's the concept of padding and the concept of multiple filters. So he's running through all of these ideas about convolutions that eventually get applied. Now, one thing that gets talked about in one of the papers that successfully applies convolutions to doing some simple tasks like sentiment classification, they use max pooling over time, and all that means is you apply the convolution, 3 filters of size 3, like we saw on the previous page, and then we get this thing here. But now, and so this is the same map that we got, but now he's taking max pooling over time. And whenever they say over time in the context of NLP, that means over the length of the sentence. And so what they're doing here is they're taking the maximum element in this column, and they're reducing this whole feature map to 1 row. 0.3 is the maximum in this column, 1.6 is the maximum in this column, and 1.4 is the maximum in this column. So that's called max pooling. So you've reduced all of this data to using a set of 3 convolution filters applied to this data, you end up with just 3 numbers if you use max pooling. So it really compactifies all of this data. Next, he says, all right, there's also average pooling. Instead of taking the maximum, like we did here, you could just take the average over each column, and then that would give you also 3 numbers. But he says that in practice, people have found that max pooling is more effective. So this is just for completeness, I guess.
One question. Yeah. Okay, so these 3 filters, so they goes one by one on our source data, and then at the end, after we have applied all the 3 filters, then we do max and average pooling. Is that correct? Yeah.
So if you look at this, let's see. Do I have a pen? Get myself a pen. Okay, so let's label this one filter number 1, filter number 2, and filter number 3. So filter number 1 gives us this column of numbers. If we apply filter number 1 to this whole thing, we get this column of numbers. Filter number 2 gives us this column of numbers, and filter number 3 gives us this column. And then for average pooling, we would basically average this column to get 0.87, average this column to get 0.26, average this column to get 0.53. But if it was max pooling, we would take the maximum of each column to get these 3 numbers. So again, the 3 numbers correspond to the three filters.
Three filters. Yeah. Thank you.
Yeah. Okay. Let's see. Back to here. Let's see. A little
What
bit
is a
of behind.
typical number of filters?
I don't know that. That's a good question. I don't know what people use. And the only way to find out would be to read some papers and see what people are actually doing.
Yeah, if you go to the next slide, I think over there we just supply the dimension of a filter. We never say what are the numbers. So as Gautam was saying, I think I'm not sure, but I'm just assuming that it's randomly initialized and it probably gets learned.
Yes, yes, that's what usually happens. Yes.
Yeah.
Yeah. So here's how it gets implemented in PiTorch. You have a batch size. You give it a batch size. You give it the word embedding size. In this case, 4. You know, the length of the word vectors are 4. But in a real case, of course, it would be 300 or whatever. A sequence length of 7. That's the length of words in our sentence. So then you would input. Your input would be random. I guess it would be a randomly initialized vector, a tensor sort of, which has a dimension of 16 by 4 by 7. So that's your input, your random input. And I guess in this case, you're actually trying to learn the word embeddings at the same time. So that's why you're randomly initializing them, so you can learn them. Then you define a convolution. There's a function conv1d in PiTorch, and it takes the input channels, which is word embedding size, output channels. That would be the number of filters that you want. And the kernel size 3 would mean that you want a 3 by 3 filter. Sorry, and this is just a one-dimensional, so it's just a filter of length 3. And then you can add the padding if you want to. There's a padding keyword there too. So this tells you how to specify a convolution in PiTorch. And so then your hidden layer would be the convolution layer applied to the input. And then the next layer would be a max pooling layer, which we saw, the max pooling operation. And that's also in PiTorch. And so you would max pool over hidden 1. Now I'm not sure what dimension equals 2 is. That's a little bit weird because there's nothing
direction?
Oh, dimension, yeah. Hidden 1.
Is that like
the direction.
On which axis you want to take the max?
Yeah, I'm not. Yeah, you might be right. It might have something to do with.
So I think in PiTorch, like the convolution is dimension 0 is the number of channels, and I think dimension 2 is the kernel size. No, or out channels.
Out channels. Okay, so.
Here
I think
0
here
is batch size, 1 is sequence length, and therefore you have to do over 2 over the second dimension, which is the dimension of the direction you're moving down, that is the sentence. So 0 is batch size, 1 is sequence length, and then
0, 1, 2.
Yeah.
So sequence length,
sequence length,
That's right. So as the first person said, the dimension equals 2 tells you which dimension you're moving the convolution over, moving the convolution filter over, and that's of course the sentence length, because as we saw this before, we're moving downward. We're moving the convolution over the sentence in a downward manner. So yeah, that solves that problem. So this is basically the machinery in PiTorch that you can use to set up these convolutions. Then he also moves to other notions that you'll see when you talk about convolutions, and one of them is stride. And let me sort of illustrate that. Get this like this. So here we're going to, if we're going to apply a stride size of 2, that means we're going to move the convolution. The first step is we're going to move for one filter is we're going to move the convolution to we're going to first overlap the convolution with the data like this. And then instead of just moving down one, the next element is going to be from moving down 2. So sorry, I drew that wrong. Let me, yeah, I got to erase. A lot of overhead in Zoom sorry. There we go, clear. I'm going to clear all that. Yeah, so, and I get my pencil back. Right, so I don't want that. I don't want an eraser. I'm sorry, I'm having a little trouble getting back to a pencil. Oh, okay. Undo, 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 undo. Okay, I've lost my pencil, but that's okay. Oh, maybe now I can get it back. Let's see. Nope. Anyway, the point is that stride 2, we're going to move downward two steps instead of 1 step. So the first convolution is going to overlap these 3 elements: 0, tentative deal, 0, tentative deal, and then the next application of the filter is going to be, instead of over the next set of pixels, it's going to, sorry, over the next set of numbers, it's going to be over the set 2 downward. I really wish I could get back my pencil. I can't get it. Yeah. Okay. Here's my drawings. Try this again. Oh, anyway, so the point is, since I can't draw it, 0 TD, the first convolution is going to overlap those 3, right? That instead of moving it down so that it now overlaps tentative deal reached, it's going to overlap. We're going to move down by, instead of 1 step, we're going to move down by 2 steps. So now the 3 elements in the convolution filter are going to overlap deal reached 2. That's what he means by DRT. And the next step, we're going to move down again another two steps instead of 1 step. And then so instead of starting with deal, we're going to start with 2 keep government. So that's the next one. And then we're going to move down 2 steps again. So the last row is going to be from government open 0. Is everybody clear on how that works? So that's what they mean by stride 2. Okay, any questions there? Okay, got to erase things.
Joseph, is it explained why it is less useful? Is there an intuition for that?
No, I don't know why he says it's less useful. I don't understand that.
Okay.
Because what it does is it compacts things for you. It can speed up computation time, because if you did stride 1 back here, you get a column of 7 by 3. If you do stride 2, you only have to deal with 4 by 3. So it, in some way, it reduces the computation. But that's a good question. He did mention in a lecture where it's less useful, so I'm not sure why. And then again, under less useful, also he has local max pooling, stride 2. So go back to our stride 2, and let's see, y 0 TD TDR. So this is stride 1. What's going on here? TDR, local max pool. So I don't know why he says stride 2, because this is from stride 1. Why is, oh wait, 0 TD TDR DRT, keep government open.
Stride 2, right? The convolution is stride 1. The max pool happens in stride 2.
Oh, okay. So here he's doing a stride 1. Sorry, he's doing a normal convolution with these three filters to give us these three rows. I'm not sure why we have infinity here, minus infinities here. Because I would have thought that we have the same result here as we had previously. Let me just scroll back up and remember what we had here. I'm thinking that the right-hand column, the right-hand object should look like this, applying the straight convolution. So there's 7 rows and 3 columns. But now he's got 1, 2, 3, 4, 5, 6, 7, 8 rows. I'm not sure why he adds this 8th row. Oh, maybe in order to do stride 2. But and then he just puts right. He just puts an extra row here in order to apply the max pooling stride 2. So how does that work? Well, we start with this. I think you need to have an even number, and that's why we had 7. He has to have 8 in order to make this work. So the first one, max pool, is looking at the max of this column, max of this, and that gives you minus 0.6. Max of this is 1.6. The max of this is 1.4. And the next thing he does is he moves this down 1. Let's see if we can do this. Nope. Anyway, move this down 2 now. Instead of moving it 1, move it down 2 so it overlaps these 6. And then if you look at this, the maximum of this one is minus 0.5, so that's what goes there. The maximum of these two numbers is 0.3, so that's what goes there. And the maximum here is 0.8, so that's what goes there. Okay, and then you can continue. And then the last operation, so you'd have one entry from here, which we saw, one row of entries from here, one row of entries for this box here, and then finally the last row would be from this box. And that's why I guess he adds this extra padding, this extra row here, minus infinity, minus infinity, minus infinity. That guarantees it won't contribute to max pooling. So the last box is take the maximum. The last row comes from taking the maximum in these columns. So minus 0.5 minus infinity gives you minus 0.5, minus 0.9 goes there, and 0.1 goes there. Okay, so it's just a way of adjusting. So he adds this, instead of a 0 padded row, he adds an infinity padded row, a minus infinity padded row, in order so that he can get the fourth output from max pooling. So does everybody see how that works? Why it's stride 2? Because instead of moving down one row, you move down 2 rows and center the filter over those pixels. So with a filter of size, with a local filter of size 2, you would have 4 entries here. Does that make sense to everybody? If you did it stride 1, you would just, I guess it wouldn't make sense to do it with stride 1 because then you would be mixing, results. Anyway, so that's local max pool. And then max pooling, and then he has Kmax pooling over time. And what that does is instead of choosing the maximum in each column, he chooses the 2 maximum elements. And he maintains the order. So in this column, the 2 maximum elements are minus 0.2 and 0.3, and they come one after the other, so he maintains the order. In this column, the maximum pieces are 1.6 is the max, and the next one is 0.6. So he pushes those in here, also maintaining the order. And here, 1.4, the maximum, the 2 most highest elements in this column are 1.4 and 1.2. So he maintains the order. So that's 2 max pooling. You can imagine Kmax pooling could be, if it was 3, then he would look for the 3 highest values. Okay, does that make sense to everybody what we just did? So it's basically the same thing we did before. Yeah. Question?
Yeah, actually, I'm just confused about the use of 2 max pooling or 3 max pooling.
Yeah, whatever K is. So I'm not sure why it would be useful, but instead of looking for the maximum, you want to preserve the first and second highest values. So instead of mapping all these numbers to one row, you're mapping them into 2 rows. And you could do the same thing for 3 max, for K equals 3 or K equals 4, whatever. So the max pooling that we learned first would be called, K would be K equals 1. We're just looking for the only one maximum value.
Hey Joseph,
Yeah.
what would be the intuitive understanding behind or rationale behind like preserving more maximum values in this case?
Perhaps you want to correct for outliers or something. Instead of just taking the maximum, which might be, the maximum might be an outlier or something. If you take the first 2, the highest 2, then you could see that by looking at it. You could see, well, the first one is, really different from the second one, so it might be an outlier. So it might be a way to correct for outliers.
Gotcha.
I mean, you could even imagine taking the maximum 2 and then averaging them together or something like that.
It's almost like beam search, right? Because you just don't want the highest necessarily all the time, and you therefore expand the search.
Yeah, that's a good point. So you don't, you allow for other possible values of. In other words, yeah. For example, the case I gave where there's an outlier, then you would see that your first maximum is way different from the next highest one. But in another column, you might see that they're very close together. So it's a way of preserving some kind of information about the distribution that you have.
Got it.
So,
Thank
as
you.
we mentioned, basically each column comes from a filter, right? So you're basically seeing whether that filter was kind of activated or not activated. So
Yeah.
if you look at like multiple values, like Srinivas mentioned, it's kind of like, was that hit more than once, sort of a thing, I guess, intuitively, if you're looking for an explanation.
Yeah, expanding on that, like you said, each column represents some kind of feature. So if you look at images, one kernel would be for identifying a certain type of feature, like maybe text or eyes or something like that. So similarly, each kernel here represents some kind of linguistic feature. So if a high value in your in the activation implies that particular feature was present at that particular spot in the sentence. So maybe keeping 2 max implies that we want to see if that particular feature occurred. If it is Kmax, we just want to see did it occur K times or something like that, whether that particular type of linguistic feature occurred this many times and how high those values are. And if I keep max, I just want to know if that particular feature occurred at least once in my sentence. Yeah.
That's a good point. Yeah, and as you said, Gautam, these convolution filters turn out to. I mean, they get solved for within the context of your backpropagation, and it turns out that these filters sometimes point to identifiable features in the text. Like, I think somewhere in one of the papers that he mentioned, the authors point that out, that some of the filters can actually be traced back to picking out things like, let's see, I'm going to think for a second. I'm trying to remember what I saw in the paper. Specific things about the sentences, like whether they had positive words in them or not, or whether they had numbers in them or not. Something like that. They pick out individual features in the sentences.
So that kind of answers the previous question, why stride 2 is kind of not that helpful, because convolution is kind of space invariant, right? If you think of it in terms of images, if you're trying to do a convolution, you're just going to try to see if the so-called feature exists irrespective of top right corner, bottom right corner, or anywhere. Whereas in case of NLP, he makes a mention that if a sentence is like positive or polite, you're not going to keep using the word polite words continuously. Polite word is going to exist somewhere in the sentence once.
Mm-hmm.
So that's why the invariance kind of doesn't transfer directly to NLP, how it works well in cases of images.
Yeah, the only thing that it does for you is it compacts things for you, and you get away with less computation. That's the only advantage I can see over using stride bigger than 1. Yeah.
So just to kind of clarify for what Raquel was saying, space invariance essentially means that only one, NLP for means that we have the relevant features that we're looking for only in one.
I'm sorry. I'm hearing you drop out. I don't hear much of what you're saying.
Oh.
Is anyone else hearing Anant and can repeat his question?
No, I'm also having issues. Yeah.
Oh, okay.
Yeah.
All right.
I can hear you now, Anand. Maybe you can try again.
Okay. Let me try again. I was just getting to what Raquel was saying about the feature being not like, okay, in case of an image, if it's an edge, it probably exists across the image. But in case of a feature in text, it might not, like what Raquel was saying, it might just be one word or two words that are not across the sentence. In that case, it's more localized, the feature, so you don't need as granular of a stride, I would think. I mean, if you take stride 3 or stride 4, maybe one of your filter catches that, and you don't need that stride 1 or something to go very granular. That kind of is the logic. Kind of get what it is.
So you're saying that the stride could be used in case when you don't really need to have as granular sort of, you don't need to go over the sentence as finely?
I mean, if I understood right what was being said, and then it kind of actually goes against the less useful version because it feels like it's more useful, higher size, because you get to pick out the rare features quickly instead of trying to do it slowly with stride 1.
I'm sorry. It looked like every second word you said dropped out, and I don't understand why. So I only heard a part of what you said.
Oh, I'm sorry. Let me reconnect or something. But yeah, please.
Yeah. Okay. When you come back, you can try to ask again or whatever.
Okay.
Okay. Okay. So we talked about local max pool stride equals 2, and then he talked about Kmax pooling over time. With K, I think we did that. Yeah. Yeah, we just talked about that. So you end up with, instead of one row, you end up with 2 rows, 1 for each maximum value. And then he talks about dilated convolutions. And so in this case, the dilation is being applied after the first set of 3 filters. So we apply the 3 filters, we get the same result that we got before. Remember, the first row starts with a -0.6, and the last row starts with -0.5. Let's just remember. Here it is again. This is just the result of applying these 3 filters. But next, he's going to apply a dilated convolution with 2 filters. So that's why there are 2 columns here. And what he means by a dilated convolution is you take the rows of the filter and you spread them out. So instead of applying the first row of the filter on the first row of the word of the sentence, you apply. Sorry, you apply the first row on the first word, the second row on the third word, and the third row on the 5th word. So you're skipping words. So let's see if we can convince ourselves that this is what we're doing here. So you would have, for the first number here, let's try to compute this number. Again, it would be helpful if I can get back a pen, but I can't.
Atrus convolutions, Joseph.
Yeah, Atrus, that's right. It's the same as the Atrus convolutions that we're discussing in the Kaggle group. It's called a dilated convolution. And so if you imagine how this works, 2 times minus 0.6 plus 1 times minus 0.5 plus 3 times minus 0.2. So let's see, that's minus 1.2, minus 0.5 is minus 1.7, minus 0.6 is 2.3. I don't understand why I'm not getting the same result.
You have to apply the whole filter on all the things, and that take the sum of that.
Oh yeah, and that's right. You have to take the sum of those. So that would be one of the numbers. You would get a number from applying these three to these three, and then you would get another number from applying these three to these three, and a third number applying these three numbers in the filter to these three pieces of the word, and then you would add those three numbers together, and it would be 0.3. So you can try that, and it should work. And then from the second filter, the same thing. You would apply these three pieces, these three elements of the filter over these three numbers, and you get a number. You'd apply these three over these three and get another number, and so on. And then you can slide this thing downward by 2 positions. So that leaves room for 2 more rows. You'll get 2 more rows if you actually complete this process. Does everybody see that? How that works, the dilated convolution?
So does this assume that the feature is kind of split across the sentence, like half of my feature is at one place and half of it is split apart from it, something like that? Why does this make sense?
It makes sense because it ranges over a wider portion of the
it's like
encompasses
increasing your receptive field in visual stuff. So you span a larger segment of your sentence by doing this.
That's right.
So by the time you get to the second set, you're spanning a larger set of, you've included the first, second, and third word, and also at the same time, by the time you convolute again, you've gone from the first word to the 5th word. So you've spanned a larger section of your sentence.
Exactly. So without doing the dilation, each application of the convolution is looking at 3 words. But with a dilated convolution, now you're looking at even though you're not looking at all 5 words, you're looking at a section of the sentence of length 5 words.
So you're doing that. The important part with that dilation is that if you think of it in terms of images, 3 by 3 would capture that region. This intuitively is actually covering like a 5 by 5 region, but you're not increasing the number of parameters.
Exactly.
So the number of computes is still remaining the same, but you're looking at a larger field of view.
Yes. So you could do this by a 5 by 5 convolution, but that would require more calculation. So that's why the dilated convolution lets you save it lets you save computation, but it's also looking at in some sense it's looking at correlations between every second word, so that it's looking at patterns where maybe a modifier modifies a word that's not right next to it but is 2 words away. So it's looking for that kind of feature, if that makes any sense. So, if you have a word that modifies another word that's not just 1 position away, but 2 positions away, or 5 or 4 positions away, then this could pick up. This structure could pick that up.
Yeah. Is this used often for images? Does anyone know?
Well, Srinivas can speak to that.
Yeah, a lot these days, especially in segmentation, and specifically because of what Raquel said, that you can cover a larger receptive field while not increasing your number of parameters. So this is especially important in segmentation because you're trying to keep the higher level context while also keeping or being aware of your low level details. And so combining the two requires that you understand the higher levels as much, that you are able to combine the higher level context with the lower level details, and the higher level contexts are usually obtained through these dilated convolutions.
Yeah, in the images, dilated convolutions can look at different scales. So, you can look at small scale features and large scale features, small scale, medium scale, and large scale features by using dilated convolutions and without increasing your computation over your computation load. So I imagine it's similar in sentences, in NLP. Okay, so as far as how the dilated convolution works, is everybody okay with that? Or if you have a question, we can talk about it more. Yeah, okay, no problem. Okay, so now he talks about this, a couple of papers. I started looking at some of these papers. Apparently in 2011, this is the first paper he mentions about the use of convolutional neural networks in NLP, but the first influential papers were in 2014, where they actually built convolutional networks, applied convolutional networks to common NLP tasks and got good scores with them. So let's see. Okay, so here's one convolutional layer and pooling. I think this is the Kim. He talks about a paper by Yoon Kim, and I think that's what was done. Just one convolutional layer, and he used max pooling. So he concatenated all the word vectors to make one long one. Concatenation of words. Okay, so then he has this notation. He introduces this notation. And the convolution filter, as we saw, has the length of k, which is the number of the length of the word vector. So it's the filter itself is 2 dimensions, but you only apply it in 1 dimension. And the length of the filter is, in the case of the simple example we were doing, it was 4. K equals 4. The number of the length of a word vector was 4. But in real life, the word vector is much longer than that. And then h is the number of elements in the length of the convolution. So in the case of what we were doing was 3. Yeah.
Right. So here's the embedding sizes. Word vector would mean number of words.
Sorry?
Word vector would mean number of words, right?
A word vector is a number of.
So xi belongs to real numbers with dimension k, is that each word has the size of k embedding size.
That's right.
There are n such words.
That's right. That's right. So in here, he actually encodes the sentence by concatenating all the word vectors. Although I'm not sure what, that's not what we did in, the examples that we looked at. So I'm not sure what advantage you gain from this kind of a notation.
I think it's because he flattens the filter.
Yeah, you could flatten the filter, but then, but then you have to be, let's see. How
would it make sense if it was stacked instead of concatenated?
If it was what?
Stacked, like concatenated vertically, you can say that. Stacked.
I'm not sure I get your meaning.
X1 below X1, then below that X2, like how it was in the example.
Yes, that's how we did it in the example. They were stacked. So I'm not sure how. Yeah, and I think that as Srinivas says, then you can make this make sense if you flatten the convolution filter. Then, let's see, how would you apply the filter? You would have to.
If you concatenate horizontally, for example, then you also have flattened the filter horizontally of hk of a single dimension. So the first k is for the first
will be like taking
word
slice of
for the length of the word vector, then the second flattened part of the filter is the second of the h dimension applied to the next k set of word vectors, and the third, and so on and so forth. So
yeah, but then it wouldn't make sense to move the convolution. You'd have to move the convolution by k every time.
Yeah.
Because otherwise you would
don't want to mix the features. Yeah, you don't
yeah,
want
you're
to
mixing the features. That's right.
I
That's
think
right. So that's one way to think of it.
Paper had a few quirky things, and since, like you mentioned, it was like one of those initial papers, it had a few quirky things in it.
Yeah. So in that sense, the filter is a vector if you flatten it out. So. Yeah.
So is the stride k here?
No, k is the length of the embedding vector.
In some sense, like what Gautam was saying is like k is how much you would move the filter.
Yes, that's right. That's right. You'd have to move the filter at least in multiples of k, right? Because
but then it seems like it's the same as the previous one. You're just implementing in a different way, right? You would have equivalent CNN.
Yeah.
So it's not different in any way, right?
That's right. It's just a different way of thinking about it, but you're getting the same numbers out. Yeah.
Okay.
Okay, so single layer CNN applied to all possible windows. Compute one channel for each layer. Okay, he adds a bias vector here, and that's not something we talked about. These are the weights of the convolution that we have to learn. And then there's some kind of a function applied to them, which I guess is a nonlinearity. All possible windows, feature map. The idea is the same as we've been talking about previously. I mean, we end up with, a feature map the same. Let's see if we can make sense out of this. N is the number of words. H is the length of the filter. Yeah. So if you have no padding, then this is the number. Then this is the number of features that you get out of doing your convolution, and that goes back to n minus h plus 1. So if n was in our example we had 7 words, and h was 3, length of 3, and then we ended up with no padding. We ended up with a 5 with a feature vector of length 5. 7 minus 3 plus 1. Let's go back and see. So here's our. Let's go to the initial case when we did no padding. There. So here's our 7-word sentence, and then we have a convolution of length 3, and we ended up with 5 possible results. I mean, we ended up with a feature vector of length 5, and that's all he's saying here. N, where is it? N minus h plus 1 is the length of your feature map. Okay, so that makes sense in terms of what we've already seen.
There is padding here. It's just that it's not symmetric padding.
I don't see any. Is that? Oh, are those the paddings?
Yeah. It's not symmetrically done where you wouldn't ideally have some padding in the front equally as what you would have in the end.
Mm-hmm. Yeah, that's weird. I don't understand that, why there would be padding here but not here. But this result, r minus, the dimension n minus h plus 1 is the result you'd get with no padding. Okay, then he talks about pooling, max pooling over time. Important. You pool the whole feature map into a single number, which is the max. We've already seen that. Using multiple filter weights. Different window sizes, h, and that means filter size. H is the length of the convolution. Because of max pooling, length of C is irrelevant. Okay, that makes sense because you're only getting one number. Yeah, somebody had a question?
Yeah, so when they say different window size, does that mean? I thought that was set.
That would be the convolution, the length of the convolution filter, which we saw in previous examples. We saw convolutions of size 2 and convolutions of size 3. So that would be the h equals 2 or h equals 3 for, you know, so here's an h equals 3 convolution, right?
Oh, the vertical.
Yeah.
The horizontal is.
The horizontal is fixed, right? It's fixed by the length of the word vector. Okay, so I'm trying to follow what he's saying here. The length of C, if you're doing max pooling, the length of the feature map is C is irrelevant because you're just taking one number from it. You could have filters that look at unigrams, bigrams, trigrams, fourgrams, etc. Yeah, I mean, a 3x3 filter. I mean, sorry, a length 3 filter looks at trigrams. A length 2 filter looks at bigrams, and he talks about convolutions of size 1 a little bit later on, and I didn't quite understand that, if anybody could enlighten us on that when we get there. And some other weird thing in this paper, and this is the Kim paper, I think. He starts with 2 copies of the input. One is, and he initializes with pre-trained word vectors, and one copy he keeps static, and the other copy he lets back propagation change the word vectors. He allows those to be part of the parameters that are being solved for. I don't quite understand the strategy or why that works or what the point of that is. Both channel sets are added to C before max pooling. So I don't understand that part.
It kind of makes sense, right? So you're trying to like create better embedding vectors for this problem, but the original one also like give you a lot of information. So you're hoping that combination will be even better.
Okay, so how are they actually combining? He says both channel sets are added to CI before max pooling. So does that mean like he averages them, or?
I haven't looked at the detail, but I thought it would be like just double the length of the vector.
Okay, so Yuri says that the reason why you keep both copies is because you want to preserve some of the features that were already built into the pre-trained word vectors, while also tuning fine-tuning them for your problem, and then combining both of those sets together. I see that makes a little sense. Yeah. Okay, classification after one. So he has one convolution followed by max pooling. We've seen that. Obtain final feature vector using M filters. Okay, so he used 100 feature maps, each of size 3, 4, 5. I assume that means that he's using 100 convolutions of length 3, 100 convolutions of length 4, and 100 of length 5. So similar to our problem when we saw here, there's 3 filters of size 3, but in that problem he's got 100 of them. And then he also has 100 filters of size 4 and 100 filters of size 2 as well. Yeah, and then one final layer, softmax, and including this bias, which we didn't talk about. So here's an architecture that is mentioned in this paper, and it's just interesting to look at because I think we can understand what it's doing. So here again we have a sentence, and again a schematic version, which is so there's only 5. The sentence is encoded by, sorry, each word is encoded only by 5 element vector. So you have the sentence matrix, which is just the input, which is all of the 7 words encoded. Then you have different size convolutions that you apply, a length 2 convolution, a length 3 convolution, and a length 4 convolution. And you can see that when you do that, you get you know, a length 4 convolution applied here gives you 4. Let's see. Why would it be 4?
Other way around, right? Length 2 convolution should give you that as the output.
Well, this is the length 4 convolution, and that's the output, right? So it would be, let's see, n, which is the number of words, minus h, which is the number of filters, plus 1. So n is 7, minus 4 is 3, plus 1 is 4. So the feature map has a length of 4. And if we do it with a 3-length convolution, then the feature map has a length of 5 by the same formula, n minus h plus 1. And then if you do it with a size 2 convolution, then you have a length of 6, n minus h plus 1. 7 minus 2 plus 1 is 6. So that tells you, and here he's doing it with multiple. So in a real situation, you might have 100 of these filters, but here he's just showing you what happens with 2 of them. So each filter gives you a feature map. Here are the feature maps from each filter. Then you do max pooling and reduce each pair of filters to 2 numbers. And so now it doesn't matter how long the feature maps were, because we're just taking their maximum. And so we end up with a pair of numbers for these two 4x4 for these 2 filters of length 4 gives us just 2 numbers. The 2 filters of length 3 gives us just 2 numbers after you do the max pooling. And the 2 filters of length 2 also gives you just 2 numbers. And then you stack them together to get 6 numbers. And then you apply some kind of a softmax to map that to 2 classes. So the architecture makes sense that way, right? And he says somehow that there's an activation function going on between. So we do more than just do the convolutions. We apply the convolution and then an activation function as well, a nonlinear function. And then to get from this layer to this layer, we do the maximum pooling. And then we get 6, and then we concatenate each one of these length 2 vectors to get a length 6 vector. And then in the final layer, we use a softmax to map that to 2 classes. So that kind of, yeah.
That the same as doing a single max pool? What am I missing here? Like he's just taking the max from each and appending all of those.
Yeah, but they're different length convolutions.
Okay, but he's still taking the max from each and appending all of them together, right?
Yes.
So it's the same as doing a single max pool.
Well, but what do you mean by doing a single max pool? Because
what is that step in the where he takes the first 2 and appends them together, and then he finally ends up appending all of them anyway. So it's the same as doing a max pool across all of the vectors, right?
Well, oh, I see what you're saying. Yeah.
What is the intermediate step where he joins 2 of them? What does that
Well,
do?
it's not really taking a max pool over this, because you have to find the maximum over this one and the maximum over this one, and that might not be the same.
And then he joins all of them. That's the same as taking the max from each and joining all of them, right?
Yes, but it's not, okay, so you could imagine stacking these, stacking this on top of this, on top of this, on top of this, and so on.
No, you don't have to stack them on top of it. Like what we saw in the previous slides, all of the kernels were stacked alongside, like as columns. And then you took the max from each and you got a new vector, right?
Yes.
Yeah, I'm saying the same thing here. Like max from each feature map, and then you are just appending all of them.
Yeah, the only thing difference, Gautam, is the length of all those are in the same. If you see the first 2 columns, whatever the colors are of length 4, the next 2 are of length 5, the next 3 are of length 6. So conceptually what you're saying is true, but you wouldn't be able to do just max of varying lengths without concatenating them, for example.
Oh, yep, got it. Okay.
Yeah. Okay, so that architecture makes some sense. And I guess I didn't look at this paper, but that's where it's discussed. Then he talks about dropout. And so this, yes.
sorry, just to add, because I was just looking at that paper, even like, and it's a sensitivity analysis, essentially speaking of what hyperparameters are most affecting the quality or the accuracy of the application. And apparently, the window sizes, the H, is one of the more important features. And a one-max pooling is good enough. It's you don't need to try and like do 2max or Kmax. One max is and that's a very interesting getting into like, because apparently the text CNN for classification is very sensitive to the hyperparameters. Sometimes it might be need to be very specific to the particular data set. So this particular paper was trying to analyze some general features that could be used.
I'm sorry. I think you had a lot of interesting things to say there, but I only caught like 30% of it because of the.
Can you post it on Slack, Anand?
Yeah.
I'll do that. I'll do that.
Yeah. It sounds like you have some interesting things to say, but dropout was being applied to your words, so I only got about 30% of them. It seemed to be some kind of a wave, a periodic wave that was going through and dropping out, pieces of your sentences. I don't understand it. Let's see, there was a comment from TWIML and he said, illustration of a CNN architecture for sentence classification, 2, 3, 4, 2 filters. Okay, so this applies to that architecture we were considering back here. Filters perform convolutions on the sentence matrix and generate variable length feature maps. That's what we saw. One max pooling is performed over each map. That's what we saw. The largest number from each feature map is recorded. A univariate feature vector is generated from all 6 maps. So there's our 6 length. Concatenated to form a feature vector for the penultimate layer. The final softmax layer then receives this feature vector as input and uses it to classify the sentence, assuming some binary classification and blah, blah, blah. Okay, so he copied and pasted from the paper. And that's exactly what we sort of saw as we went through this. Yeah, so that makes sense. So let's see now, he's saying, so the dropout is also a hyperparameter, the probability of, they use a Bernoulli random variable, which means you drop something with a probability, with some probability, and so you have to find that value of p that is the best, and you do that by tuning the hyperparameter. Let's see. So this tells you, so this R apparently, or this Z is some kind of a map of the dropout that takes away, some of the inputs from this linear transformation. So again, dropout is something known from image convolutions, and it's got a regularizing effect, and it works apparently the same way in text problems. And just as in image problems, you don't use dropout at when you're doing inference. Let's see, but you have to scale. I guess you have to scale the final vector because you only used some fraction of your inputs, and so you have to scale the final vector to get it to agree. He also had this weird thing. This is from the Yoon Kim paper, where he constrained the weight vectors to have a certain, I think, norm S, where S is the norm of the it's a limit for the norm of the feet of the weight vector. So I think if any weight vector had larger values, he did some kind of truncation or rescaling it. I see. He rescaled the weight vector so that it doesn't go in excess of, it doesn't go any larger than S, where S is some hyperparameter that has to be chosen again. Not very common. I guess this is something that he used in this paper, but this is the Yoon Kim paper that hasn't been used very commonly. So these, yeah.
So how is that different with the clipping? Like, you know, the parameter clipping we do, or a weight clipping. So isn't that something similar?
It does seem to be, yeah.
Gradient clipping, right?
This is not for the gradient.
Yeah. Sorry?
This is different. That's a gradient clipping, so that's when you're doing backprop. This is not during your backprop.
But it might have the same effect so that it prevents the gradients from exploding.
Gradient explosion has no connection with this as such, right? It's if you actually calculate your gradient is when you are doing the update. You don't want that to be too large to move you away from where you are. At least that's what my understanding was.
Yeah, that's true. What is their logic is, instead of clipping the gradients, you clip the weights beforehand so that the gradients don't explode. Like, this is just a hypothesis.
Yeah, I'm inclined to think that this has something to do with preventing gradient explosions. Yeah, but there's two regularization methods that apparently are used here. One is the dropout, and the other is the weights normalization, or weights clipping somehow.
I have another question. That's the with regard to the dropout. So it says at the test time, no dropouts, and scale final vector by probability p. So what the final sentence? What does it mean? Scale final vector by probability p.
Well, if you use dropout in your model, then since you're using fewer inputs, your outputs are going to be smaller because you haven't used as many of the inputs, and they're going to be smaller by some factor p, where p is the probability of dropout. So you have to scale so that when you don't use dropout, you have to correct by some kind of a scale factor. And I thought it would be 1/p, but so I'm not sure why he used p.
So this scaling is the weight vector. So the weights need to be scaled by p.
Yeah, yeah, and p is the same as the dropout parameter, the probability of dropout that you've used in this in the dropout portion of your training.
Okay. Yeah. Thanks.
Okay, and so here's a summary of all the hyperparameters that were used in the Kim paper. Let's see, for nonlinearities, he used the ReLU. Window filter size is 345. Each filter size has 100 feature maps. He used 0.5 for his dropout parameter, and he reported a 2 to 4% accuracy improvement. And then he used S equals 3 for the to make sure that the weights didn't get too big. He used a mini batch size of 50, and he used pre-trained word vectors from word2vec with length of 300. So yeah, and it seems like Manning was a little bit he sort of deprecated Kim's result a little bit, saying, yeah, he beat us. You know, he noticed that he beat a lot of the results from Stanford groups. And he said, yeah, he beat us because mostly he got it from the dropout. He said, if we would have used dropout, we would have been better by that much too. So it wasn't really fair of Yoon Kim to say that he beat all these other methods, because they didn't use dropout and they could have. So apparently
Joseph,
that's what
could
he
you
was saying.
go
Yeah.
back to the previous slide?
Yeah. This one?
So yeah, shouldn't it be the opposite? Like, you scale up the vector when you do dropout, and during test time you don't have to scale up, right?
Yeah, that would make sense. That would make sense. You scale during the
Training.
During the training part, and then you don't have to worry about it during test. Yeah,
That's
either
wrong,
way.
right?
So, and also I would think that you have to scale by 1/p at test time if you're doing it that way. Yeah, but that's a good point.
So what is W here? I think I missed it. W is
The the final softmax layer, I think.
so it's not the weight,
WC.
right? It's the activation, right?
It's the softmax weight.
Uh,
Row in the softmax weight. So back to here. So you apply a softmax to this to get this.
okay. So dropout is applied on the softmax, on the final concatenated vector, right?
That's what I read into it. Yeah.
Yeah, so I think it's like when you've got dropout, if you've got like P set to 0.5 when you're training, that means half of your weights are going to be missing when you're training.
Mm-hmm.
And so the output you'll get will be half the size that it would be if you had all your weights present. Therefore, at test time, you need to effectively divide by 0.5. So if you multiply by 0.5, that reduces your output back to the same values you were getting at training time. So if P is 0.5, your output will be
Yes,
half
that's
as well.
right. So to compare apples to apples, you have to scale. If you're doing it at test time, you scale by P. But if you were doing, I think it was Gautam suggested that you could also do the scaling at training time, and then you would scale by 1 over P. And that way
Yeah, you can do it both ways.
Yeah,
so
and that way you'd be comparing apples to apples.
Yeah, so at training time, you're not actually scaling by P, you're dropping out P connections.
Yes.
So as I say, if P is 0.5, half your connections have gone, so you get half as much output as you would if you had all the connections.
Right, so you multiply it by 2 to make that correction.
Yeah, so usually what we do is the activation is what's scaled up and scaled down. So here we scale down the weights apparently. So that's why it's P into. But if we were to look at the activation, during training, it would drop, it would reduce because of the dropout. So you scale it up by 1 by P, I mean by multiplying
Yes,
them. Here we are
that's right.
scaling down the weights. Yeah.
Exactly. So if you want to do the correction at test time, you multiply by P. But as Gautam suggested, you could also do the correction at training time, and to do it that way, you would divide by P instead, and you'd get the same result.
But you would do it on the activation, not on the weights.
On the activation, not on the weights.
Yeah.
I'm not sure how that.
Because your activation, so during training, your activation values on average is smaller than if dropout was not applied. So
Yes.
you would have to increase your activation value, which is, so you would have to increase the activation value by multiplying it by 1 by P.
So that you're saying after you do the activation, then you multiply, then you scale it back up.
Yes.
Yes.
Like
okay.
You multiply W into X and then you get an activation. That activation's average value would be lower if you were applying dropout. So you increase it by multiplying by P. Yeah.
Exactly.
And
that's
this
right.
wouldn't be applied at the last layer, right?
Apparently, that's what he's saying. It's only the softmax layer.
Because if that's the case, then if you think of the classification example, if you chop off connections, then you won't have like 10 classes at the end, right? If you're chopping off connections, you would have less than 10 classes.
So dropout is applied on the concatenated vector, right? That we
Right.
saw.
So that's what. So not the.
No, not the final one. The concatenated vector.
I'm not sure what you mean. You mean this one?
Yep. Dropout is applied on the concatenated vector.
That's right. That's right. And then you still map it to 2 classes. Okay, so here is all the experiments that he talks about, and I don't know all of these, but let's see. CNN random. So there's random initialization. This means that you randomly initialize the word vectors and you let the network solve for them. Here's where you take the pre-trained word vectors and keep them keep the pre-trained word vectors. Here's where you start with the pre-trained word vectors and let the network improve them. And here's where you use 2 channels, as Yuri said. You use the original pre-trained word vectors plus the trained, fine-tuned word vectors, and you combine them in some way. And I'm not sure what all these are different NLP tasks and the scores that you get on them. And it's kind of interesting because on this particular task, I'm just looking at it carefully. The static pre-trained word vectors where you don't try to improve on them got the highest score here. Although these scores are close, but that's just interesting. And so there's a bunch of other techniques which I don't know the names for, but notice that there are a lot of them are from Stanford guys. Socher is from Stanford. There's a paper that he refers to. Oh, here's Manning also. So Manning's involved in a lot of these too. And there's a paper by Kaltschbrenner that he refers to, dynamic CNNs. I didn't have a look all the way through. I just kind of looked at it a little bit. Let's see. I guess these are other different techniques. And I'm not sure what all these tasks are. He talks about it in the paper. But yeah, and here's where he's a little bit miffed that, that the comparison wasn't really apples to apples because Yoon Kim was using dropout, and a lot of these other methods didn't use dropout but could have, and presumably therefore they would have been better and maybe have beaten Yoon Kim's. So he was sort of a little bit miffed about that. But he still gives them credit to that from a simple architecture like CNN, they were able to get really good results. And one of the things that is pointed out is that there's nothing added. I mean, the network solves for everything. You don't have to have going in like parsed information like keyword, like what do you call it, named entities, and other parsed information that sometimes gets used as input. The network figures out everything for you. I'm looking at one of these. Let's see, somewhere in here, one of these papers they mention that. So in Yoon Kim's paper, he says, despite little tuning of hyperparameters, a simple CNN with one layer of convolution performs remarkably well against all these other methods. And some of these methods use extra information that he doesn't use. So he just uses the pre-trained word vectors as input. Anyway, let's see, model comparison. So the rest of this, let's see what he thought. Oh, he talks about these gated units used vertically. This is something we've seen before. I mean, when we looked at, if we took Jeremy's class, whatever, we saw these residual blocks where you skip levels, you process an input through some layers, but then you also add it back at the end so that you don't lose the initial information. So that's called a residual block. And then there's something else called a highway block where you do a similar thing, but instead of just putting this through some layers, you have a final layer where you use another function to map it. I'm not exactly sure what this T of X or what the C of X is, but so it's a little more complicated, but it's the same idea as the residual block. I think, Srinivas, are you working with highway networks when in your segmentation problem?
No, the highway networks we touched on in the BIDAF paper. So there's actually an image of the highway block and a description of it that's relevant in the BIDAF links. I think that either the second or the third page of the BIDAF discussion, which we had, I think, last week or 2 weeks back, and that explains the simple way to understand it is it's a combination, just like it of the input and a transform version of the input. And the residual block just simply combines f of x and x, and this thing introduces another variable that you can tune as to how you can combine f of x and x, and t of x and c of x are computed. And as I said, the BIDAF discussion has better explanation of that.
Okay, do you know what this dot means when you say x dot c of x?
I think it's just a multiplication, frankly, and that happens on both. So I don't know why there's just a dot on that one.
Yeah. Okay, so he talks about using gated units. So they're basically applying stuff that they found out works with images, and they're applying it to text problems, and they're finding it that it's also giving advantages. Batch norm is another concept that comes from images, or at least it first came from images. Convolutional networks scale the activations to have zero mean and unit variance, and you update every batch. Makes the models less sensitive to parameter initializations. Makes the tuning of learning rates simpler, and apparently PiTorch has this available for 1D convolutions as well. So batch norm is available for use in NLP problems. And then this last part of 1x1, let's see how many we have left. 1x1 convolutions, I don't really understand what the point is. Does anybody understand 1x1 convolutions and can explain them? What's to be gained by a 1x1 convolution?
In Vision, it's usually used to just change the number of layers and keep your kind of H and W constant. And as he says, conceptually, therefore, I look at it as just being, a fully connected network, which just helps you change the number of channels. So you can think of it kind of similarly in this case. It just helps you change vary the number of channels while keeping H and W the same for an image. In this case, it again will only help you change the number of channels that you're using.
So you're just basically taking linear combinations of the words in some way. Because if you
linear combination of the features, right?
Well, if you apply a 1x1 convolution to a sentence,
yeah, you wouldn't usually do that. It's much towards the end, and that's why the fully connected layer is what is important to notice here. If you were to do it the same way with the fully connected layer, again, you'd use a ton more parameters because of fully connected. Like it sounds as like every connection has to be made. Whereas if you do the trick with a 1x1, it's kind of like that bottleneck stuff where you're squeezing down, or at the same time, you can increase the number of layers.
So let's go back and see. So in a problem like this, here he applies a length 3 convolution, and then after that a length 2 convolution, and you're saying that the 1x1 convolution would be applied at the end here instead, something like that.
Right. And in this case, it's not really a 1x1 convolution. It's more like a 1, right? Because it's not 2D.
Right. So a 1. So right. It's just basically if you have one of these, you're doing nothing. If you have 10 of them, then you're basically having a linear combination of the feature map, of this feature map, right? With 10 parameters.
Yes. You're combining those 10 feature maps into whatever, let's say 3 new feature maps. Linearly combining that to give you 3 feature maps. So you're squeezing down the number of layers. Or you can go the other way also. You can bump up the number of layers.
Okay. Okay, so practically I don't see how that works, but it's good to be aware that it exists.
Yeah, the practicality is like the number of computations. And the reason why you usually would want to squeeze and unsqueeze is kind of like, think of it like in the residual connection scenario itself. Let's say you're going one way and you do a bunch of convolutions and you, for some reason, your number of filters increase, right? Now, if you're coming down the other direction and you want to concatenate both of these, rather not concatenate, sorry, to add both of these, you should have the same number of filters and the sizes need to be the same. So size you can do by upsampling or downsampling. How do you change the number of filters if you wanted to add both of them? That's one place where a one-by-one, this network-in-network situation can help.
Mm-hmm. Okay. Talk about one-by-ones. Okay, and then let's see. I didn't really get past here in the notes here because it looks like you have to go and look at these papers, and I didn't have time to do that. So if anybody else did, you're welcome to talk. He talks about the last part. He talks about character level, using character level instead of word level representations. But I didn't really go over it. So let's see. Then he also talks about very deep convolutional networks. I think in with this trick of residual nets, they were able to go very deep in, have very many layers. So you have ResNet and so on, and ResNet 101 and so on. You can have very deep nets, very deep convolutional networks, and this has been used for image processing for computer vision. He says also they've been using that in text as well, but so far, at least as of 2019, they weren't able to get. I think he talks about 29, a network that's 29 layers deep, and that going deeper didn't help or didn't make things better. So at least that was in 2019. But apparently these residual net concepts can help in NLP problems as well. These residual block concepts and batch normalization and so on can help you to build deeper networks for NLP problems as well as computer vision problems. And yeah, so I didn't go any further than that. So I don't have anything to say about the last part of this. Yeah, so that's where